So the session is actually expected to be for like total 2 hours, but uh, so the general idea here is that as a teaching assistant for this course, I'll be clarifying any doubts if you have for the week one content, and if you want, I have some extra problems also ready, so we can take a look at them. Or I have another option like I will share something from my research and which is somewhat in line with whatever is taught in that week's course. So, can I just get a poll of what you guys would like to? Which option would you like to have? Like, would you like to, or maybe we will first go through your questions for the week's content, and then we can consider some extra questions or whichever one you want. Hello. Can you please explain through your research? Okay. Yeah. Sure. Okay. So. Okay. So most of you guys would like to see something from the research applications. Okay. Okay. So, but none of you have any doubts regarding the week one's content or anything? Okay, no doubts. Okay, fine. So, just a small intro of myself. So, I'm Vallabh Devakar. I'm a BTech plus MTech dual degree graduate from IIT Madras, and currently I'm pursuing a PhD in ocean engineering department. So, that's just the brief intro. And so, actually, the week one's content was mostly on topics related to the tools that are usually used in machine learning. So you saw all these tools that are very popular in machine learning, the linear algebra basics, norms, so on, and uh, yeah, matrix decomposition and stuff. Yeah. So one of the applications is that I worked on during my research is something called dynamic mode decomposition. So maybe I can share my screen through that.
Balab, before that, can you please start recording?
Yeah, I have recorded. I'm recording on OBS Studio my entire screen.
Okay. Thank you.
Is everyone able to see? Okay.
Yes, yes.
How do I automatically up? I have to individually admit people, I guess. But yeah. There must be some setting. just give me a few minutes, guys. I think a lot of people are joining. Okay. I guess this is really good. So I'll give a very brief intro of this topic because I we probably can't go into the full detail maths of it right now. But yeah, so one of the applications of the singular value decomposition, which we studied in this week's content, and its application to fluid flows has been through this process called dynamic mode decomposition, and I worked on this last summer. So this what you are seeing here is actually a velocity field of flow past a cylinder, and this is like a canonical problem in fluid flow. So what they try to look at whether when the flow is moving past the some spherical bluff object, they will look at how the vortex trading and the characteristics of fluid flow happens, and that is so this is kind of used as a benchmark for like checking if there is any new algorithm, let's say developed for doing computational fluid dynamics. They will test it with this scenario. So it's like a benchmark problem in CFD. So in this session, we'll be looking at it as from a perspective of data perspective, not as a. Am I audible? Feel like. Hello?
Yeah, you're audible.
Yeah, okay. Yeah, so in this session, we will primarily look at all of this as from a data perspective, not from a like the computational fluid dynamics perspective. So what you are, as I explained, this is a fluid flow or past a cylinder, and the data for this was generated from a code called IBPM, and it's a solver basically. It solves the 2D incompressible Navier-Stokes equations, and the flow is simulated basically. So in the start of the course, you kind of saw how data is being processed. So here we are kind of looking at the flow field as a image. So instead of considering the flow fields like, so a flow is basically characterized by the velocity of the particles in along the x direction and y direction. Instead of that, we are kind of looking at this as a picture basically. So at every maybe I will show the animation, and you can get a better picture of this. Yeah, so yeah, so as you can see, this is kind of the how the flow field is actually being visualized. So as you might see here, these green blobs, they are like being shaded, right? That is called the vortex shading phenomena. So and the flow is moving in this direction towards right. So this is the data that we have. So it's like a movie of flow past cylinder, and we are going to use that and try to understand whether how that will help us get some understanding of this phenomena itself. And we will use the tools for like the tools that you studied in this week's content, and see how they are traditionally applied to such problems. Is anyone speaking anything? Because I'm not able to hear anyone.
Too much of noise is there.
Uh, is my voice low?
Too much of noise.
Noise. Oh, probably from the fans.
By the way, have you just started this? Because I just joined at 6 and it
Uh,
was already demonstrating.
Hello?
I said I joined exactly at the 6 o'clock. So have you started it before? Have I missed anything?
No, no. This is just the starting point.
Okay.
So basically, I asked people like what they would like me to cover here. So uh, uh, the these weekly sessions are actually supposed to be like doubt clearation sessions, and I I basically asked what you guys would like to go, have for this session, and some students they told that they would like to hear some of the applications of the content that was studied in this week content. So I'm basically covering something on those lines that I have worked on in the past.
Okay.
Which course meeting is this? Okay. So this is the meeting for machine learning for engineering and science applications. Uh, is the Rakshit Upadhyay answer for you. So I will be going through the one of the applications for uh, the content that you studied. So you studied some concepts like singular value decomposition and use of matrices to represent data and so on. So this particular application that I'm showing on the screen is kind of using all of those content. So uh, the what we'll be discussing on is something called a technique called dynamic mode decomposition, and it's a application of single value decomposition.
Vallabh, I think your voice is suddenly spiking up and then it is suddenly going down. I think it's a problem from the microphone that you are having. So, can you please correct that?
Oh, okay, okay, sure, I'll try. Mm.
Well, one more question. So, the agenda in the email says you are explaining some problems that will be helpful for the weekly assignments, but here you are explaining about the project and the code.
Yeah,
So, is
so
this the right meeting that I have joined, or am I missing anything?
no, this is the right meeting. Maybe so. I asked some people who joined initially what they would like me to cover today, and they said that they would like me to go through some research topic. But if maybe I will take the poll again.
Okay,
Uh,
no problem.
if the majority of the people want here for some doubt clarification, I will first prefer that to be done. Okay, I'll retake. So maybe just put in the chat what you would like this session to be about. So options are like whether you want doubt clarification or yeah, this is my first session also actually. So whether you would like doubt clarification or some extra content or okay doubts assignment question doubts okay. Okay, majority are now doubts. Okay, so fine. That's better.
Yeah, because we don't want a new topic to be started. So whatever that was covered in week one, maybe if we can talk on that only, that will help us for the assignment stuff, is what I feel.
Okay, sure, sure, no problem.
The first problem I faced actually when after setting up, it asked me for a license, and if I trying to put the license key which is shown on the MATLAB console, it is not accepting that. I don't know whether I'll be able to still solve it or not.
Uh, MATLAB. Okay. Actually, I have not gone through the MATLAB setup procedure. We'll first clarify some technical questions,
Okay.
like
Okay.
if someone has, then we will maybe come to the MATLAB. Assignment 1, question 6. Can you please
1 to
walk
6.
us through it?
1 to 6.
All 1 to 6. Okay. Ideally, the thing is, I am not supposed to share the solutions of the questions.
No need of solution. At least how to approach and those kind of stuff.
Okay, okay. So maybe my screen is not visible.
So, for example, there are some problems related to eigenvector and all, where we have not covered those kind of things in the class actually. So, only the concept has been explained. Maybe some sample problem might help.
Okay, okay. So then we can, yeah, this is being recorded. So okay, maybe we will try to get a poll of concepts that would like to be covered here. Everyone is okay. Question 6 seems to be very popular. What is this? So it's the week 1's question 6 that is being asked. Computer product of A and B resulting in matrix C. Okay, okay, yeah. This was one of the questions which had a discrepancy in the options. So I think this will be clarified in the like in the discussion forum. So for now, I think you can pass this question.
Which one? Which one will be covered in
The question 6.
Okay. How about question 3? They have given some eigenvalues, and for that eigenvalue, we have to. What is the question?
Okay.
So we have to find the inverse of the matrix. So we don't even know how to approach this problem.
Okay, so maybe then I will discuss the concept of eigenvalues. Will that be okay?
But some sample problems also has to be worked on, right? So without, I don't know.
Yeah. So I will discuss some basic idea about the eigenvalue problem, and then maybe that will give you some ideas about how to approach this.
Yeah, sure. Yeah, thanks. Or are you saying that if you understand the concept, you should be able to solve the
Yeah.
problem
Yeah.
by yourself? That's what you're saying?
Yeah. Is this visible? Yeah, I guess it is. So the general eigenvalue problem for any matrix A is actually defined as follows. So the A is a matrix and X is the, let's say, an unknown vector, and lambda is a scalar. So the eigenvalue problem is essentially this expression that you are seeing here, and all the solutions of X that satisfy this equation for a scalar lambda are going to be the solutions of this eigenvalue problem. Okay. So in lines, I'll give some ideas about how the solution is usually found out for this kind of problem. So what they do is you can write the lambda as lambda times identity matrix and multiply that with x, and that doesn't change the right hand side at all. And you can then keep the left hand side just as this. So you have ax equal to lambda I times x, and you can just take the right hand side, everything from right hand side to the left hand side, and you end up getting a minus lambda I into x is equal to 0. Okay, so the as you must have studied this in your high school maybe. So to get a solution for this equation, a non-trivial solution is only possible when determinant of a minus lambda I is 0. Hello? Who are asking, maybe they can keep responding.
Go ahead.
Yeah. Okay.
Go ahead, Vallabh.
Okay. So the idea is that you want to essentially solve this expression now. Determinant of a minus lambda I is equal to 0, and lambda is going to be the unknown here, and you will essentially try to find all the lambdas. So if we'll take some example here. So let A be some for example 2 cross 2 matrix maybe. Two, three, 4, 2 maybe.
Sir, are you showing question number 6?
Yeah, I'm not specifically going to solve the questions because that doesn't serve the purpose of the assignments. So I will try to give some hints towards the way you are supposed to think to solve the answers. Okay.
Okay, sir. Please give some hint to means most of the questions so that we can solve.
Yeah, sure.
Okay, sir.
I will go one by one based on the popular demand of questions. So the expression that I wrote above.
So identity matrix, second row, second column.
Yeah. Thanks. This is supposed to be 1. So this we ultimately end up getting a form such as this. And you are essentially going to find the determinant of this thing, and you want that to be 0. So and now you can see here that so this lambda is now having so this is a quadratic in lambda, so you can have multiple values of lambda that will satisfy this. In the question that you are seeing in the assignment, they have mentioned that there are 5 different values of lambda, which means there are the so this expression that I have written here, the quadratic, so that is called the characteristic equation of the problem.
So we should also take any 5 by 5 matrix, for example, and then we should evaluate to the eigenvalue whatever they have given. That's what you're saying by using the formulas, whatever you suggested above.
Yeah, I mean that can be one of the ways, but the problem is actually a bit simpler than that. It actually asks you to think about the implication of having a 0 eigenvalue.
Mm-hmm.
So
Okay.
I mean, that is the hint I can probably give at this point. So you have to basically consider the implication of 0 being one of the eigenvalues of the matrix A. Okay.
Okay.
Can you explain how the model takes input vector, process that vector? Can you please clarify this question? I'm not completely understanding it. Can you explain how the model takes the input vector, process that vector? Sai, can you please clarify your question? Hello? I mean, it being called specifically the winter of AI or anything that has, it's just a, I mean, it has no real significance to the concepts of AI specifically. It's just about the period being not that active in the sense. That's all. I mean, it has. Uh, this is the answer to Durga's question. Yeah, I mean, it has no specific significance to AI concept specifically. It's just historical names that they have given for it. Can you go over how to calculate eigenvalues? Okay, so do you want me to go over this this specific thing that I showed just now? Harshit.
Hello, sir. Am I audible?
Yeah, you are audible.
Sir, I want to know that what is the significance of this eigenvalue in the vector matrices processing in machine learning?
Okay, so specifically for machine learning, we will have that in a. You will get that experience a bit in different contexts. So, but eigenvalues and eigen vectors are actually very core concepts from linear algebra, and there they play a very important role. So, maybe I will after I will, someone is asking for going through the content that I've just covered, so I will just go through this and then I will try to explain some of the uses of eigenvalue and how they what is the geometric or intuition behind it.
Thank you, sir.
Okay, so I'll just go through whatever I've written so far. So the eigenvalue problem is essentially defined as follows. The first line that you are seeing over there, ax equal to lambda times x, where lambda is going to be a scalar, a is a matrix, and we are essentially interested in a vector x which satisfies this expression and its corresponding lambda value. So we can essentially write the right hand side as lambda times I times x, because identity matrix times vector is still going to be that same vector, and lambda is already a scalar, so it doesn't matter. And this part is being just rewritten. The right hand side is just being rewritten as lambda ix, and then you can just take the entire right hand side and put it to left, and you will get this expression, which is a minus lambda I times x is equal to 0. Now a trivial solution for this is obviously that you just put x equal x, all elements of x being 0, and this equality will be directly satisfied. But we are interested in the non-trivial solutions of this expression. So non-trivial solutions are only possible if the determinant of a minus lambda I, which is this thing, if that is equal to 0. And
So
then,
in the sorry.
yeah.
Sorry, in the problem, whatever they are given is the eigenvector, right? So we have to find the matrix or the scalar. What we have to find out?
No, the question that is given in the assignment is actually you are given the eigenvalues. So there are 5 different solutions of this eigenvalue problem is what they are telling you. Okay. And there are 5 different lambda values that are satisfying this. In the question they have like, if I remember, -1, 1,
So we have to
0.
find the matrix, right? We have to find the inverse of A, right? Matrix we have to find, right?
No, I mean, you are in. The question is asking you to find the eigenvalues of the A inverse.
Lambda.
Yeah, the lambdas of A inverse. You have been given the lambdas of A. You are asked to find the lambdas of A inverse.
Okay, okay.
Okay. So I'm just going over the procedure of calculating these lambda values. So in general, if I'm taking an example here, 2 cross 2 A matrix, 2, 3, 4, 2, and so there is a lambda value which does satisfy this relation, and the determinant of this resultant thing is going to be 0, is what I mean. We are interested in that lambda which actually does ensure this.
So we can also assume a matrix
Hello,
of 5 cross 5 here, right?
Yeah, you
hello,
can
sir.
assume a matrix, but okay.
Hello, sir.
Yeah,
Am I able? Sir, I want to ask that. Um, sir, in a matrix, in a vector, if we say that it has a rank 4, it means that it is a independent row vector set. But in eigenvalues, sir, what is the meaning of the eigenvalue?
yeah,
It
yeah,
means if we say the eigenvalue of the matrix of A is 2, what does it mean that?
yeah. I will go through the actual intuition behind eigenvalues, but some people were asking about how to calculate the eigenvalues. That's why I was just going through this example. I will just come to the intuition part right now. Okay.
Okay, sir.
Okay, so whoever was asking about the method of calculating the eigenvalues, just I'm just completing this part here. So you basically solve for lambda in this expression, this lower expression, this quadratic. Now, this is a quadratic because we have only 2 cross 2 A matrix. It can be any order polynomial, and this is essentially called the characteristic polynomial. Okay, so you try to find the solutions of lambda for this expression, and that is going to be the eigenvalues for this problem. So I will now try to uh, cover some intuition of what an eigenvalue and eigenvectors really mean, uh, and maybe I will also recommend a source for any of you who are more interested in looking at some visualizations and stuff. So if you are familiar with this channel, YouTube channel called 3 Blue 1 Brown, that channel has a very interesting video of several linear algebra concepts, and particularly about eigenvalues. So I would highly recommend anyone interested in knowing or seeing the visualizations of this stuff to go through this video. So I will just cover the from what I understand about the eigenvalues, and I'll try my best. So the eigenvalue problem is actually defined as follows: ax equal to lambda x. So one thing that you have to now know is that whenever a vector is multiplied with a matrix, the matrix is essentially trying to rotate and scale that vector. Okay, so you have to, I will maybe note this point down. Matrix vector product is equivalent to scaling and rotating a vector. This not a vector, maybe you should say the vector. Okay, so this is important intuition that you need to realize for the further discussion. So remember this: a matrix vector product is essentially going to scale this. So let's say A is this matrix and X is this vector. So this vector is now going to be scaled in the sense, so if I just have this vector over like this, the scaling of this vector means it can either shrink or it can expand. Okay, but a matrix multiplication not only does this, it could also end up turning the vector around to in some other direction. Okay, so
Yeah.
so far okay.
So here we are doing both, or as per this equation, we are only rotating lambda times, right?
No. For now I'm focusing only on the left hand side. I'm only talking about what a matrix vector multiplication is about. So a matrix vector multiplication is essentially scaling the vector and also rotating it. Okay.
Okay.
Okay. So now there are special matrices. So essentially, if this is a vector for, let's say, a 3 cross 1 vector, and this matrix is a 3 cross 3 matrix, so there can be any 9 numbers filled in this, right? I mean, this could have been any 9 numbers in the real world, which can be multiplied with this. So now these 9 numbers, if you choose in a specific manner, you can actually ensure that the vector is only rotated. Okay, and that is basically what rotation matrices are about, if you are familiar with rotation matrices.
Yeah.
So there are certain special matrices which have a property called orthogonality, and their norms being 1, that will ensure that any vector multiplied with them will just be rotated. It will not get scaled. It will not change its length, basically. Okay. So maybe I will just note this down. Special matrices can only or maybe special matrices only rotate rather than okay. So this is one of the special matrices considerations. But what the eigenvalue problem is actually talking about is an even different scenario. Okay, so eigenvalue problem is actually maybe I will again write it over here. Ax equal to lambda times x. What this side is that it tells that I'm multiplying a vector x with a matrix A, whatever will be my output. So now this has to be another vector, right? So if you do a 3 cross 3 matrix multiplication with a 3 cross 1 vector, you are ultimately going to get a 3 cross 1 vector, right? So what this is telling is that ultimately this is so for a matrix A, so this is actually a special property of the matrix A itself. Okay, so I choose a matrix A and I fill all these. For this video I am going to be considering a 3 cross 3 matrix because it's easy to demonstrate on this. So for a 3 cross 3 matrix A, there is going to be a special vector x, which when applied, so this x when I multiply with the matrix A, I still remain along the line of the x itself. That is essentially what lambda times x means. Lambda times x means lambda being a scalar and x being a vector means this right hand side is actually a vector which is still along x. It may either get shrinked or expanded, but it's still along x. Is that part clear?
Yeah.
Sir, it means it cannot rotate.
Hmm?
It cannot rotate.
Yeah. So for the A matrix, this x is a special vector, which when multiplied with A is still giving a vector which is along x itself. It is not rotating it. Okay. So I mean that is essentially what the intuition of the eigenvalue problem is, and to really understand how this gets applied to various concepts in uh, like machine learning, maybe I think this will get more better covered through some other content in the later weeks. So for now, this is probably the intuition that will suffice for at least this week. So you just need to know that the eigenvalue problem for a matrix A is essentially the fact that there exists a special direction x or vector x, which when multiplied with A will still put me along the vector x itself. It will not throw me off and change my direction. Okay. Is this enough of the intuition, or do you have any questions? I missed a lot of things.
So the lambda is the factor.
Yeah, lambda is the scaling factor. Yeah, so lambda is the factor with which this
Uh,
vector x is getting shrinked or expanded, but it's still along x itself.
yes.
Okay. So I seem to have missed a lot of chats here. Hmm. How to calculate? Okay, eigenvalue calculation is done. Activation key. Okay, MATLAB problems will be resolved later. Problem number 5, please. Okay, problem number 5. What is this? Okay. Consider an orthogonal matrix. Okay, yeah, essentially that is what I just talked about. So A transpose A being equal to identity means that it won't scale a vector that is being multiplied with it. I think this is getting has already got resolved. Problem number 5, Pawan Kumar. So I'm leaving the meet because okay, fine.
So for an orthogonal matrix, can we take an identity matrix as an orthogonal matrix while solving the problem?
I mean, identity matrix is a very special case of an orthogonal matrix. Ideally, to talk about something in general about orthogonal matrices, it would be better to not take an identity matrix. In fact, you can try to use some rotation matrix. So if you are familiar with rotation matrices, I think that will be better choice for choosing something more general about orthogonal matrices.
Okay. So you are suggesting not to choose an identity matrix in
Yeah, I
case.
mean, identity matrix is a very special case, right? I mean, if you end up getting if something does end up satisfying for an identity matrix, it need not be sure that it's not guaranteed that it will satisfy for anything else, right?
Okay, because that is easy for the multiplication.
Yeah, yeah. I'm okay. What is Hadamard product? I think this is covered in the week's videos. Maybe you can just go through that. Sir, can you please explain eigen decomposition and singular value decomposition once more? Okay. This I will do once again. Explain linear independence and span. Okay. How do you verify? So not if eigenvalues are given like the last option. Okay. Yeah. The A inverse question. It's up to you to try to figure out the implication of having a zero eigenvalue. So I won't reveal the answer, just like, I mean, then it doesn't serve the purpose of the assignments. Giving inputs are changing into vectors. How does it take the vector in training time? I'm still not getting what this means. Okay, it's okay. I just okay. So question 2 is left. Singular value decomposition is to be discussed, and linear independence and span. So maybe I will start with linear independence and span. So before we jump into, okay, span and linear independence, they are very closely related. So we'll just start with an example itself. Some special numbers, 2, 4, 0. Okay, just for the sake of this example. So, or maybe I should better keep it to 2D for now. Okay, so just imagine a matrix which is this kind of matrix 2 4 1 2. Linear independence or linear dependence essentially means that this column of the matrix can be written as a is essentially a multiplication of I mean, this is just related by a factor of 2, right? So this what linear independence and span and all of these concepts essentially try to talk about is, so given this matrix, you can start imagining a vector space defined by the columns of this matrix. So what do I mean by a vector space defined by columns? So imagine this matrix. So I have a Cartesian system over here, and I'm going to put 2 comma 4, which is a point here. 1 2 3 4, maybe I should put it here. Okay, and I have a 1 comma 2, which is going to be over here. So if you try to imagine a vector which is along 1 comma 2 and another vector which is along 2 comma 4, this both of these vectors are along the same line, right? So big, and it's obvious because they are just a scaled version of each other. So what this means is that now if I wanted to, let's say, express a point somewhere else, let's say I wanted to express this point 3 comma 1 in terms of these two vectors. So I would do something like this. So I'm basically saying that a linear combination of these two vectors, whether there exists a solution that will give me this answer. So can I express this 3 cross 1 vector as a linear function of a linear combination of these two vectors, 2 cross 4 and 1 cross 2. Okay, so if we try to really solve this thing, what we will end up getting is 2a plus b equal to 3 and 4a plus 2b equal to 1. And oh wait, something is wrong. essentially, yeah. So if I just from the bottom equation I just take 2 common, I'm again going to end up getting 2a plus b. Okay, so I've just rewritten this equation again. I started with 1 and 2 and I've rewritten 2 into this form. And from the first equation we know that 2a plus b is equal to 3. If that is supposed to be satisfied, then 6 is equal to 1, which doesn't make any sense, right? So there is no possible linear combination of these two vectors 2 4 and 1 2 which can give me this another point 3 comma 1 in the same space. So the point is that if two vectors are linearly dependent, which they are for this the two vectors 2 4 and 1 2, if they are linearly dependent, you would end up getting a space which is not like spanning the entirety of the 2D. So any point along this line, which is this line, you can express it in terms of the linear combination of these two vectors, but you can't express any other random point in the 2D world using a linear combination of these. Okay, and for all such points you are going to end up getting such weird needs, and that is definitely not going to be true. Okay, so essentially what I wanted to conclude here is that having linearly dependent vectors reduces the span of the space. Okay, span is essentially all the other points in the world that you can reach. Okay, as for example here we took 3 comma 1. If someone maybe we can have a question and answer here, so that will cover this part better. Hello. Sai Kanna, you asked about linear independence and span. Sai Kanna, how did you get
Yes,
3
sir.
comma? Oh, okay, yeah. I just randomly chose a point 3 comma 1. It could have been any point in like 2D place in this plane. The point is that any point apart from the points along this line is not going to be. It's not going to be possible to express that point as a linear combination of these two vectors.
Yes, sir, I got it.
Okay. Yeah, rank of matrix is a very related concept. So for this specific matrix that you are seeing here, 2 1 4 2, the rank is essentially reduced. So ideally we would have liked the rank to be 2, but because the columns are dependent, the rank is now reduced, and that relates to span and linear dependence.
So for the final assessment, sorry for the deviation. So for the final assessment, it will be like we have to do it in MATLAB, or it will be like the assignment kind of whatever we are going through the assignment, that those kind of questions, or it will be like we have to do it in the MATLAB.
Usually the NPTEL exams, they happen MCQ questions types only. As far as my experience is, but I will confirm with the course instructors as well whether for this course they are planning to take MATLAB also into account.
Okay, thanks.
So will there be any
Except
programming assignment in MATLAB? That means in Python I did one course. There was means one non-proctored assignment exam also. Will there be something like that in MATLAB?
I will check up with the instructors. As far as I know, that is not there, but I will confirm it rather than. And any of the all of this information will be shared through the announcements. So you just keep an eye out on that.
Okay, sir. You take class on every Monday. You will take class.
Yeah, I'll be taking every Monday. Yeah.
Okay, sir.
I seem to
Hello,
have missed.
is there any course project?
The course doesn't specifically expect you to do any additional projects, but you are free to implement the stuff that you learn in the course. So the course will not like grade you for any projects also.
Okay, thank you.
Vallabh sir, can you please put some light on the final exam, the pattern? It would be a descriptive or an MCQ based.
Most likely it will be MCQ. Uh, I mean that is my experience with previous NPTEL exams, but if the instructors decide this time they want to change it, they might change it. But all of this will be told quite beforehand, before the final exam. So it will be announced in the course
Okay, sir. Thank you.
forum. Yeah.
Sorry, it's a bit out of topic, I feel, but still, I just wanted to check with you, since you know better on this. So, like, how is it different from the as I don't know if it doesn't make sense. Please, you don't have to answer. So, how is it different from the other courses? Like, I mean, like what? How much we would be confident? See, for example, this is a 12 weeks course, right? So we have to put some amount of effort and we have to get it done, get through this. So how can we compare this with the other courses in the market? How competitive is this?
Uh, I mean, in terms of competitive, I mean, it's not about. It's not about competition in general. So,
Okay,
as far as an individual, you just have to attempt the exam and score as much as you can. So,
okay.
and
So so
you still
so
get
in
selected.
case okay, so in case if we get through this, then we would be able to solve the real world problems, like maybe in our organization.
That I think would depend more on uh, if so the course will cover a lot of theory of several important concepts in machine learning, and it's not really possible to get a hands-on on all of them in the course time duration. And I mean 12 weeks is really a short time for such a thing. But once you have gone through the course, if you do some projects and based on the concepts that are covered here, I think that will help a lot.
Okay, okay. Thank you.
The video YouTube.
Sir, in the final exam, means the questions they will be means we can expect questions similar to the assignments.
Yeah, I mean, uh, yeah, similar to the assignments in the sense the concepts will be exactly. I mean, we won't go outside the concepts that are taught in the course, so it will be in line with the concepts.
Sir, in the assignments. Okay.
Sir,
Yeah.
will this lecture be uploaded in YouTube?
What?
Will this lecture be uploaded in
Yeah, yeah. This lecture will be uploaded in YouTube. Yeah.
Sir, before 2 days, I believe I think one lecture has been conducted, but still now we did not get.
Uh, okay. I mean, it will be uploaded on my YouTube channel. That is what I am expected to do actually. Uh, if maybe I will when I upload it in the next meeting, I will put the link of the video of previous lecture, if that works.
Hello.
What about previous lecture?
Yeah, this is the first lecture. I mean, this
No,
is my
no, no.
first
Hello.
lecture.
I think on 20, from 6 to 8, we have solved 4 problems in a PDF, right?
Okay, so there are three different teaching assistants for this course who will be
Yes.
taking these online sessions. So I'm not aware of what others are planning to do, but they will also
Yes,
be
sir.
expected to share their uh, recordings.
Yeah, they told
Oh,
that they would share, but till now we did not get any mail or something, and it's been 2 days. That's why only I got it out.
Hmm, maybe next week you can just ask them to share their recording.
Okay, sir. Thank you. Thank you.
hello, sir.
Yeah.
Uh, Sir, can you explain the norms? Okay,
Norm.
sir. Yes, sir. Sir,
Yeah.
we get to know about it that it is the root of the square of the dimensions
Yeah. Yeah.
in a vector.
Okay.
Uh, what is the intuitions behind? And
So norms in general are actually, so you can think of norms as a generalization of the distance. Okay, so when we have a vector in 2D, we look at its Euclidean distance, which is like how far the endpoint of the vector is from the origin, right? So that is something which is in 2D only. So I mean, it can be in any D actually, but so this particular definition of having measuring the distance of a point from the origin based on the, I mean, the Euclidean distance of it. So that is particularly called the L2 norm. And so what happened is that along with L2 norms, they kind of try to generalize the entire concept and uh, consider different versions of it. And that is what the different norms L1, L infinity, and so on are actually about. So, I mean, there is nothing much by. I mean, the definitions of these things are covered in the course. So, I can't specifically tell anything more than the definitions of this. Would you like me to cover the definitions?
yes, sir.
Okay. Okay. So L1 norm essentially is actually, let's say you have a vector x which has several components. Okay. Maybe we'll call them x1, x2, x3. So x is now an n-dimensional vector, so it has n components. So L1 norm is of this vector is going to be defined as the summation of absolute values of all the components. I mean, that is just the definition. I mean, I can't specifically tell anything more than the definition of these things.
And here we have to take the absolute values, right?
Yeah, here we look at the absolute values. In L2 norm, you basically take the square root of the sum of their squares. And so you try to expand this so definition. So what this actually ended up being is actually something like this. So I'm doing summation xi raised to some, so if I'm taking a pth norm of a vector, what I'm doing is xi raised to p, and I'm taking going the sum of this, and I'm going to raise it to 1 by p.
Sir, what is the physical meaning of this norm? I mean, like in the lectures, it was something related to, like, take an example of an image, and he told something. It's some volume or something. Is it the physical meaning of it?
uh, I'm not very particularly sure of how that relates to the volume. I mean, there is actually a flaw. I mean, I'm not completely sure that part, but I will check up on it and maybe I will cover it in the next class.
I mean, sir, in the lecture, he told it was like stretching and rotation. By proving some theorem, he told that take the eigenvalues, make it a diagonal value, and then multiply a matrix with A and A inverse before behead and ahead, so that we can rotate and stretch it and make the matrix equal. Like basically to find out difference to, I mean, in between two images, in between how to check the raw data of two images. Like in such a way he has explained. Like we do not actually know. He told that in coming lectures it would be explained. So I just so okay, no problem. Sir, no problem.
Yeah, if it is going to be covered later, I think we'll both look at it.
No, I mean in the videos recorded, already recorded videos, it was told that it will be taught. I mean, this is the next lecture, right? So I was asking.
Yeah, I mean the lecture will so all of this image related stuff is going to be covered in around week 6, where the convolutions and all of that stuff will be discussed in more detail. So I think more on this will come at that point.
Okay, sir. Thank you.
Sir, what is the actual difference between Frobenius norm and L2 norm?
So yeah, I mean it's just a different terminology for different type of input. So I'm defining an L2 norm for a vector. I'm defining Frobenius norm for a matrix. That's all.
Okay, sir. And sir, what is the relation between the invertibility of a matrix and the dependency of a matrix? So how it affects? So whether a matrix is invertible or not invertible. So how it affect the dependency of a matrix?
Yeah, essentially, so uh, a matrix having linear independence of linear dependence of its columns or rows essentially leads to its determinant being 0. And if you know the way to actually calculate the inverse of a matrix A is actually 1 upon determinant of A times the adjoint of A.
Into adjoint of A.
Yeah.
Yes.
So uh, having a determinant 0 ensures, I mean, means that the matrix, the inverse of the matrix doesn't exist.
Okay, I got it.
Yeah. So with this lecture, yeah, lecture will be uploaded to YouTube. Have I missed any other questions? Yes, the lecture is being recorded. Yes. I'm recording it on my system side. So are there any other questions that I have missed?
Sir, question number 1. Can you see assignment 1, question number 1? It's I'm finding it confusing.
Actually, this question is actually very simple. It's just, I mean, they have tried to make it sound difficult, but it's actually very simple question. So you have a input of size 1024 cross 8, and then you are supposed to multiply it with something, and the output is supposed to be something. So essentially this is about checking what matrix multiplications are valid. Okay, so maybe I'll just give a rough idea.
Sir, sir, can you brief out?
Can you
the
give
topic?
another example?
Yeah, I'll just cover this part. So if I have a matrix A which is an m cross n matrix, so m cross n means it has m rows and n columns. Okay.
Okay.
And I have another matrix B which is, let's say, n cross k, and all of these m n k and m n and k are, they are different numbers. So a matrix product of this type is defined and it's valid. I mean, if you even in any programming language, if you try to multiply a matrix of this type, you will get an answer. But if you try to do it other way, so let's say B was a matrix of size k cross n, and or any other number, doesn't matter. But if n and k are not the same, you can't possibly multiply these matrices. Okay, that's the entire idea.
Okay, okay, sir.
So, and the question is actually exactly about this point: which matrix multiplication is valid?
Sir, can you please check out the
Sir, question number 2 is assignment.
One at a time, please.
Yes, sir. Can you please check out the question number 6?
Question number
Because I
six,
have
yeah.
done it.
Question number six has
Yes,
ambiguity. It will be cleared. Uh,
I have done it through trial and error method. I'm not getting the exact answer.
yeah, yeah. There is an ambiguity in the question. It will
Okay.
be clarified through the
Okay.
announcements.
Sir, question number
Okay.
2. Any hint for
Question
question
number
number 2?
two. Just let me check once. Yeah, this is also about the same idea. Uh, you have to essentially check what is a valid matrix multiplication, and so uh, AB transpose actually is A being an n cross 1 vector. So, uh, yeah, I mean, this is actually a. So, what they essentially wanted you to know is that if you try to do this thing, so am I my screen? Okay. So, A being an n cross 1 matrix, a n cross 1 vector is actually like this. It has n rows and one column only, and B transpose, which is now going to be 1 cross n, which ends up being this. So now the way this is defined, this product is defined, is that you take the first element of A and you take the first element of B, product, multiply them. That will be the first element of your output. Then you multiply the first element of A with the second element of B, and that will be your second output. So essentially, the first entire row is actually a scalar multiple of the B, and it's multiplied with the first component of A, and all of these later rows end up being just like that. So there are different scalar multiples of the same B. Hello?
Okay, sir. Thank you.
Yeah.
Sir, in question number 8, question number 8, there is something called intensity of self interactions. What is that? Can you please tell? Hello, sir.
Question
In
number
question
8.
number 8,
Yeah, yeah.
there is something called intensity of self interactions. Can you please explain that?
Yeah, I mean, it's just a thing that has been defined for this specific question. Am I audible? Yeah. I'm talking about question number 8. So they have defined the intensity of an interaction, self interaction, as the trace of the matrix M. The trace essentially means sum of the diagonal elements.
Yes, sir. Sir, can you please explain, means give some hint and explain how? Yes,
Yeah,
sir, 8.
yeah. That's the whole point. Like they have defined the total intensity of self interaction as the trace of the matrix. So you are essentially asked to see whether the trace of matrix M and M transpose, are they same, different? What are they? I mean, how are they related? I hope this clarifies it.
Yes, sir. These topics are clear now. You can proceed.
What?
We understood what you said just.
Okay, okay, good. Okay, good. Yeah. Anyone else having any doubts? I might have missed in chats.
Sir, singular value decomposition.
Okay, yeah, singular value decomposition. So the singular value decomposition is actually a generalization of uh, something called spectral decomposition. So, but I will limit the discussion only for singular value decomposition for now. So, what this essentially says is that if you have any matrix A, and A need not be anything like square or anything like it can be any matrix, like absolutely any matrix, size m cross n, and you can essentially break down A or decompose it as this form, and this is a theorem, so we can't go through the proof of this thing, but you have to believe in this equality that any matrix A can be resolved or decomposed into three matrices of this form, U, sigma, and V transpose, where U and V are something called the unitary matrices, but for real A matrices this will be orthogonal. So U and V are orthogonal. Okay. And sigma is a diagonal matrix. Okay, so this is just the definition of what a singular value decomposition means. To just tell a bit of intuition, I can give small amount of it. Like, so we studied that a matrix A, when it is multiplied with a vector x, or if when you are asked to calculate something like this, what this essentially does to vector x is that it scales and rotates it, right? So that phenomena can essentially be broken down with this decomposition, is what singular value decomposition says. So if I try to break down A as per this thing, I will end up getting U sigma V transpose times x. And so if I so as we studied before, like an orthogonal matrix is that special type of matrix which only rotates a vector. So the you can imagine that the rotation part is now separated, and when you multiply anything with a diagonal matrix, it will scale it along all the dimensions of that thing. So if this was a diagonal matrix, so there are non-zero values only along the diagonal, and if I have any vector over here, and if I take the multiplication of these two, I'm always going to get a scaled version of the quantities on this vector. So what singular value decomposition essentially is doing is that it is separating out the rotation and scaling part. The rotation part here is firstly taken out from V transpose x, then you are scaling it, and there is another rotation that brings it back to, I mean, it doesn't bring it back, but so there is another rotation that is happening. I think for this I can actually refer to YouTube video series which does very nice visualizations of this singular value decomposition. I will search for the link. Yeah, I'll share the visualization.
Working professionals, do you
Yeah, three blue, one brown's man name is being used in this thing also. Yeah. So, I mean, this will give you a much better idea of what singular value decomposition really is than I can explain here. Can we get recorded lectures of this session? Yes. This will be uploaded on YouTube, and you can, or maybe I will just share my. So, as a part of this teaching assistantship, I'm actually expected to upload these recordings to
Sir,
YouTube, and I will be uploading it on my own YouTube channel, and I will try to make a playlist and organize them. So, whoever is asking about the recording, it will be on that YouTube channel. Can we discuss your notebook on ML problems? Notebook on ML problems. Okay, the applications.
Yes, sir.
Okay, we'll see if someone has any questions, and then we will go to that.
Sir, explain eigen decomposition.
Yeah, I mean, I would rather recommend this YouTube playlist actually, because they give a far better uh, visualization intuition for the thing. If anyone has any questions, do let me know. For singular decomposition, I am kind of redirecting you to a different playlist, because I think they will do a far better justice on the topic. Okay. If anyone, so I'm assuming there are no more doubts.
Hello, hello.
Yeah.
Yeah, good evening, sir. Sir, actually, I have an question. A tutorial video provided by by the course, uh, and that is MATLAB. Okay.
Okay.
Can we do same thing through Python, and can we get the same means video tutorial that that is related to, means that we can do through Python?
I mean, you can implement the stuff that is shown through Python also, but I mean, the course is actually kind of recommending you to use MATLAB, because probably they have some codes uh, which are already written, and you don't have to like recreate all of that stuff again.
Okay.
So it would be better if you can use MATLAB. Or else you can also try to recreate that on your own in Python, and I think that will be a much better learning experience.
Okay, okay, fine, sir.
These weeks being the of basics. Will these be a part of final exam, and also what is generally the format of? Usually the course is of the final exam is of MCQ type, but it might or might not change depending on the course instructors. So it will be announced in the announcement section for this course. And probably, I mean, the exams actually try to cover the entirety of the course uh, content. So you can expect some questions from this part also. Okay, so are we having any more doubts? So I'm assuming all doubts are covered for the week's content.
Hello.
Hi.
Yeah, hi, Vallabh. This is Jayant.
Yeah.
Can we discuss the question number 6 in
Yeah,
the assignment?
the question number 6 is having some ambiguity. It will be clarified in the announcements.
I see. Okay. Thank you.
By the way, everyone here is checking out the discussion forum also, right? There is a discussion forum for the course, and I mean, most of the doubts that you ask are regularly, I mean, textual answers of those are also available in the discussion forum. Okay, if there are no more
Sir,
doubts,
how can we access the discussion forum?
the discussion forum, if you open the course page, there is a at the top there is a ask a question link. It will redirect you to the discussion forum for machine learning, for engineering and science. Or maybe I can just share this link also. Yeah, I've shared the link of the discussion forum also. So, are there any doubts? Okay, if there are no more doubts, I think we'll have that. I'll cover the applications part that I was actually starting at the start of this meeting. So this is not actually a part of the course, but I mean, just to give you guys an idea of how the concepts that are covered in the course are applied in these like engineering applications. So this is just an example of it. So I will just restart this again. So one of the classical problems in or rather a benchmark problem in fluid flows is actually this flow past a cylinder. So they usually use this as a test of so any new algorithms that they let's say develop for uh, uh, computational fluid dynamics. So they try to verify that algorithm's correctness by comparing it against different. So this is like a canonical problem to just test whether the algorithm is doing its job correctly or not. So is there a comment? Can you share the collab file? Yeah, I will share it sometime later probably because I'm still working on this thing. Is that fine? Okay. So the idea here is that we are looking at a tool called dynamic mode decomposition, and which is based on the concepts of single value decomposition, and this can be used for like essentially predicting in future about some physical systems. And as I go through this tutorial, I think I will be better able to explain that. So here is a like a video of what this flow phenomena is actually like. So what you are seeing, this green blobs actually getting shed out from this uh, behind this cylinder, is something called the vortex shedding. And uh, so the visualization that you are seeing here is actually the coloring is actually just denoting the directions of the uh, net velocity of the flow. So it might not feel like look like a real fluid flow. That's because this what is being visualized is not really the fluid flow itself. It's just the color is based on the gradient. The color is based on the direction of where the flow is pointing towards. So the bluer the flow, bluer the color, that means they are aligned along the same directions, and redder means the flow is moving in the opposite direction of the blue direction. Okay, and this is just a visualization of what that flow is like. So this tool called dynamic mode decomposition is actually like trying to simplify, or rather get a like a spatio-temporal simplification of the actual fluid flow. So, and in singular value decomposition, you must have studied about like, so this previously what we saw, the sigma matrix, which is the scaling part of it. The singular value decomposition is actually ensures that the part of the so the bigger singular values will be in the start of the matrix, and the smaller ones will be towards the latter part. So it is actually what in a simplified form, what this actually does is that it gives you the more dominant parts of the data, and it highlights them out, and you can see them as superposition of different modes. And I'll probably show you this. Yeah. So whatever you are seeing there, this flow in time, is actually a kind of a superposition of this kind of spatial what can I say, spatial modes basically. So this eigenflow field 0 that you are seeing here is the most dominant pattern in the spatial pattern in the entire flow, and the flow field 1 will be the second most dominant, flow field 2 will be the third dominant, and so on. So what this actually allows us to do is that so you can essentially I will have some more clips here. I will try to tell what is the difference between all of them. Okay, so notice the first clip and compare it against the second one. You can see that the second one is not very accurately depicting the first thing, right? So that is actually about this thing is actually kind of taking a simplified version of the real data, and it's trying to predict what is actually happening based on that simplified version. And what we are essentially seeing is that a way too simplified version, which is using only one dynamic mode, is not effective in capturing the real physics of that is happening in the system. Then if we look at the other video here, which is having three modes being used, you can see that this matches better to the first one, and the third one, which is having 6 modes. Okay, this is not looping. Yeah, the 6th one is far better matching the first one, this one. Okay, so what this essentially is about is that single value decomposition and all of these techniques are actually something called data compression techniques. So instead of trying to represent a phenomena with a lot of information, you can just extract the important aspects of it and still get out the exact same phenomena. In this reality, in this the actual thing that this flow is actually capturing is actually having 151 modes, but it looks like even the top 6 modes are able to capture the phenomena decently well, and that is something what singular value decomposition is essentially telling us. I probably can't go through the entire mass of it, but my interest was just to give a idea of what this can do. And the technique dynamic mode decomposition actually goes a step further beyond single value decomposition. And what it does is that you can limit the amount of data in time. So what you are seeing here is actually a clip of a movie of flow field, right? So if you keep or give the model only a few, like let's say this has 151 timestamps, and you give only the first 100 time steps, it can on its own predict what the next 50 are going to be like. So that is one of the use cases that was explored in this study. Yeah, in the first video of this week, you actually saw how an image can be used to uh, uh, like send the input for a machine learning model, right? So in this case also I was doing the same thing. So all the snapshots, so like individual snapshots of this flow field. So the flow field is this thing. So what we are doing is we are taking snapshots at every time instant and looking at that image. So we are trying to feed the images to predict next images only. Okay. So the image data is essentially a series of pixel values, and you can just uh, rearrange them into a very tall vector. So this particular image, which is one snapshot of this, has 199 rows and 449 columns, and this can be rearranged into a much longer vector of this size. And there are such 151 images, which makes the entire movie of that you are seeing below. And you can rearrange all of these long vectors, and this essentially becomes your data. So the tool, in the start of the week, the first video, you saw that how image data can be used. So this is one of the ways it can be used. I think I can't go through the entire detail of this maths because it will take a long time. Okay. So if anyone has any questions about this, I think that will be a better and more interactive way of discussing this. Hello? Can you define the problem / investigation of this study? Okay, so it was just about the tool called dynamic node decomposition. So what that allows us to do is that the physics that is really happening is like a very complicated physics pattern. So the flow is moving past a cylindrical object, and it will do all sort of things, the vortex setting and all of that. But our goal is to see whether there is any dominant pattern in this flow phenomena and capture that. And that is essentially the goal of the study in very short terms, if I wanted to say. And that those patterns are not only in space, we are also looking at space and time, if that helps. Practical application, any. Okay, so DMD, the technique that I'm talking about, it has several applications. This particular is not actually a application per se. It's just a academic check, I would say. But in reality, DMD has lot many applications. Maybe I can share a YouTube tutorial on this. So if you want to know more about the dynamic mode decomposition technique, you can refer to this video. Any other questions? So we'll be closing at around 8. What are the resources for learning machine learning with CFD? Yeah, so you can actually take a look at the above video. So that video is actually from a professor's channel. His name is Steve Brunton, and he has excellent resources on this topic. Can you share the textbook? Which textbook? If you are talking about the textbook for written by that professor, it's actually freely available on their website. Maybe I can share the link of that as well. Yeah, I think it should be sufficient. I mean, if you have any more doubts, I think maybe, if possible, I will see if the next tutorial I can take MATLAB also. But in that case, I won't have enough time. But okay, let's see. Weekly version will be on quiz one day. Yeah, I mean, practice notebooks is, I mean, amongst yourselves only. If you want, you can post them on discussion forum, and if you get some like a group, you can discuss amongst yourselves. So you can use discussion forum for Are there any more questions? Maybe then we can wrap up. So, I mean, I'm not I'm not sure how eligible I am to answer this question, but one good approach would be probably to try and see some collaborative projects if you can get. So, from your background, if you find some professors in IITs or something like that who are working on similar ideas that you want to explore, you can try to get projects with them. Assignments, I'm not sure whether programming ones will be there in the course or not, but as far as I know, most are MCQ only. Yeah, you can. Yeah, this course will cover the conceptual application, conceptual parts of machine learning, and uh, often it will not be restricting to applications only. It will rather focus more on the theory. Yeah, I mean, if you are familiar with physics informed neural networks, I think that is one of the ways people are looking at solving CFD problems. Shall we acquire problem solving skills? Yeah, I mean, you'll get familiarity with the concepts and you can then apply them to whatever problems you are currently working on. I mean, it's up to you. Look from the looking at the content of the course, you can choose for yourself like which one is more aligned with what you want to study. Continue this course. Yeah, you can continue the course. I mean, there's no harm in doing the course, right? Also, by the way, you can see the videos of the previous offering of the course on YouTube. So if you have any doubts like what all will be covered in future weeks, you can already look at that. Probably not programming assignments, but I'll confirm once with the instructors. So maybe I should start noting down all the questions that I have got about exams and stuff. So will we learn about deep learning applied on computer vision problems? Yeah, I mean, one of the topics covered in the course is convolutional neural networks, which are essentially what deep learning applied to computer vision. Can whoever had some questions about the exams and stuff like that, can you just re-ask those so that I will just note them down and I'll ask the instructors. By the way, you can also post all of these questions on the discussion forum. I think that will be far better. Yeah, I mean, as I said, better to ask all these like exam related questions on the discussion forum, since the instructors will be looking at those. What are the required skills for getting job in machine learning? I'm not a eligible person to answer this question, but I mean, the field is growing so rapidly. You just have to keep learning, I think. I think if there are no more questions, we can. It's almost time. Tell some main skills what you know. Okay. Uh, I would say uh, having a conceptual understanding of the main concepts like which are probably even covered in this course. Uh, Having the ability to implement them for your own problem statements. So you should basically try to explore different problem statements on various concepts, and in fact try to look at some problem statements which use multiple uh, tools, like maybe you can look at reinforcement learning and computer vision both together or something like that. I mean, having good projects is probably the best way to get to, I mean, present yourself for a job. Okay. So we'll be stopping, I think. Thank you all for joining.
Okay, that very